Single stage transistor amplifier. In a single stage transistor amplifier, only one transistor and its associated circuitry are used. For a practical transistor amplifier, it consists of biasing circuit R1, R2, etc. The input capacitor is used to couple the signal to the base of the transistor. If it is not used, the signal source resistance will come across R2 and thus change the bias. The capacitor Cin allows only AC signal to flow but isolate the signal source from R2. Emitter bypass capacitor CE is used in parallel with the emitter resistance RE, which provides a low reactance path to the amplified AC signal. If we have not used CE, then amplified AC signal flowing through RE will cause a voltage drop across it, thereby reduce the output voltage. A coupling capacitor CC, which used to couple one stage of the amplifier with the next stage. If it is not used, the bias condition of the next stage will be drastically changed due to the shunting effect of the collector resistor RC. This is because this RC will become parallel to the upper resistance R1 of the next stage. In a amplifier there is AC component and a DC component. So base current will be a mixture of base IB, that is DC current, and AC current. We will represent as small I capital B. Similarly, collector current is capital IC plus small ic, that is small I capital C. So this emitter current is IE is equal to IE plus I capital E. Here I have given an input signal. The output is like this. In the positive half cycle of the input signal, the current increases, the base current increases. Since the base current increases, the collector current also increases because IC is beta IB. Since the collector current increases, the voltage drop across RC also increases, that is ICRC increases. Since ICRC increases and VCC is a constant, the output voltage VCE decreases. Or in other way, I can say when the input signal increases in the positive half cycle, the output signal increases in the negative way, or the input voltage and output voltage have a phase difference of 180 degree. We can prove it mathematically also. So the total instantaneous output voltage VC is VCC minus ICRC. If you differentiate dVC is equal to VC is a constant, 0 minus dICRC. Change in VC is equal to change in IC into RC with a minus. This minus gives the output voltage is 180 degree out of phase with the input signal, or the phase difference of 180 degree between the signal voltage and output voltage in a common emitter amplifier is known as phase reversal. So in a common emitter amplifier, there is a phase reversal of 180 degree between input voltage and output voltage. You can prove it graphically. So this is the VC IC graph. Here AB is the load line. Base current varies about 10 microampere, that is a maximum of this one plus 5 and a minimum of minus 5, that is IB maximum is 15 microampere and minimum is 5 microampere. IB is maximum, see the point G, VC is minimum. When IB is minimum, this value graphically it is clear, VC is maximum. That's the idea. When IB is maximum, VC is minimum. When IB is minimum, VC is maximum. So it is very clear that these two are to have a phase difference of 180 degree. This is a circuit and all I have given here. Q value 10 microampere. It changes 50 microampere and 5 microampere. The beta value is 100. 10 into 100 microampere is equal to 1 milliampere. That is the IC. 15 into 100 microampere, that is 1.5 milliampere, and similarly 0.5 milliampere. This is the output current. So let us calculate the output voltage. The output voltage VC is equal to VCC minus ICRC. When IB is equal to 10 microampere, then IC is equal to 1 milliampere, beta IB. Therefore VC is equal to 10 minus 1 into 4. 4K is the RC. that is 6 volt. So this is the base 6 volt. Similarly, when IB is equal to 15 microampere, VC is equal to 4 volt. This is the minimum. So this is when 15 microampere minimum. When IB is equal to 5 microampere, VC is equal to 8 volt maximum. So mathematically also it is very clear. There is a phase difference between input voltage and output voltage. See, the input current and output current have no phase difference. They are in phase. In a transistor amplifier, there is both DC and AC conditions. The DC source set up DC currents and voltage, whereas the AC source produces fluctuation in transistor current and voltage. To analyze the action of the transistor, it is better to split into two parts. One is for AC analysis and the other is for DC analysis. Okay, this is a circuit. Here there is both DC and AC stages exist. First we are going to make a DC analysis. For that we must have a DC equivalent circuit. In order to get a DC equivalent circuit, first reduce all AC sources to 0 and open all the capacitors. Okay. First reduce all AC source to 0. So make signal 0 and open all capacitors. So it will look like this. VCC, there is no source, no capacitors. Okay, there is no capacitors. So this is called the DC equivalent circuit. Similarly, for an AC equivalent circuit, reduce all DC sources to 0, that is VCC 0, and short all capacitors. Okay, not remove, short all capacitors. This is the AC equivalent circuit of this amplifying circuit. Load line analysis. First, DC load line. So this is the circuit. So this is equivalent DC equivalent circuit. We have VC is equal to VCC minus IC into RC plus RE, where I have choose IC is approximately equal to IE. Therefore, this is the DC load line. And this is VCC and VCC by RC plus RE. AB is the load line. Q is the Q point, 0 signal point. VC is maximum when IC is 0, that is VCC, this point, and maximum value of IC is when VC is 0, that is VCC by RC plus RE, that is this point. These 2 points constitute to the DC load line. An AC load line, the line on the output characteristic of a transistor circuit, which gives the value of IC and VCE when signal is applied. This is the AC equivalent circuit and this is the AC load line. Maximum value of VCE is VCE DC value plus IC or AC, and maximum value of small IC is equal to capital IC plus VCE by RAC, where RAC is RC parallel RL, that is RC RL by RC plus RL. Voltage gain of amplifier is the ratio of AC output voltage to the AC input signal voltage. This is the AC equivalent circuit. AC load RAC is RC parallel RL, that is RC RL by RC plus RL. Output voltage V out is equal to IC RAC. Input voltage V in is IB RIN. Voltage in AV is V out by V in, that is equal to IC by IB into RAC by RIN. That is beta. Beta is IC by IB. Beta into RAC by RIN. Power gain is AP is equal to IC square RAC by IB square RIN. That is beta square RAC by RIN, where beta is IC by IB. Multistage transistor amplifiers. In a multistage transistor amplifier, there is more than one transistor amplifier circuit exists. It's like that. Input is there is a first stage and a coupling, and connected to the next second stage, coupling, third stage, output, etc. So this is a 3-stage transistor amplifier. In a multi-stage amplifier, there is different stages. The different stages are coupled by some coupling. A coupling is mainly used to transfer AC output of one stage to the input of next stage, to isolate the DC condition of one stage from the next stage. There are 3 different amplifiers. When we use RC coupling, it is called RC coupled amplifier. When you use transformer coupling, it is transformer coupled amplifier. If it is direct coupling, it is called direct coupled amplifier. Decibel power gain APdB in decibel is 10 log AP, that is 10 log P out by P in, output power by input power. A decibel voltage gain AVdB is 20 log AV. 20 because power is I square R. Bandwidth, the range of frequency over which the voltage gain is equal to or greater than 70.7% of maximum gain is known as bandwidth. So this is a graph connecting gain and frequency. This is called frequency response of the amplifier. This GM is the maximum value. This is the 70.7% of GM. So this is F1 at this point F1, this is F1 and F2. F1 minus F2 is known as bandwidth, where F1 is lower cutoff frequency, F2 is upper cutoff frequency, and FR is the resonant frequency. At resonant, it have GM maximum value. Suppose GM is 100. So this value is 70.7. So fall in voltage gain is 20 log 100 by 70.7. This is equal to 3 dB, or we can say this is the 3 dB point. This is 3 dB point. Therefore, bandwidth can be defined once again as bandwidth of an amplifier is the range of frequency at the limits of which its voltage gain falls by 3 dB from the maximum gain. RC coupled transistor amplifier. In resistance capacitance coupled amplifier, the different stages of the amplifiers are coupled with a capacitor. This is a two-stage RC coupled transistor amplifier. This is the first stage, this is the second stage, and two transistors. That first stage is coupled with the capacitor CC. Suppose G1 is the gain of the first stage and G2 is the gain of the second stage. The gain of this two-stage amplifier is G is equal to G1 into G2. If you are calculating in decibel, G is equal to G1 plus G2. Its operation is the AC input signal of the first transistor gets amplified and appears at RC, which is then passed through CC to the next stage. This becomes the input of the next stage, whose amplified output again appears across the collector load RC. The total gain is less than the product of the gains of individual stages. This is because when a second stage is made to follow the first stage, the effective load resistance of the first stage is reduced due to the shunting effect of the input resistance of the second stage. Its frequency response is this one. Here the reactance Xc is 1 by 2 pi Fc. At low frequencies, that is less than 15 Hz, Fc is low, therefore Xc, high reactance of Cc causes very small part of signal to pass from one stage to the next. And due to the high reactance of Ce, emitter capacitor, it cannot shunt the emitter resistance effectively. At high frequency greater than 20 kHz, the reactance of Cc is small and behaves as a short circuit. This increases the loading effect of next stage and serves to reduce the voltage gain. Along with this, as the capacitance of emitter diode decreases, it increases the base current of the transistor, due to which the current gain reduces. Hence, the voltage gain rolls off at high frequencies. At mid frequencies, between 50 Hz and 20 kHz, the voltage gain of the amplifier is constant. It is flat. If the frequency increases, the reactance of the capacitor Cc decreases, which tends to increase the gain, but this lower reactance increases the loading effect of the next stage, by which there is a reduction in gain. Advantages. The frequency response of RC amplifier provides constant gain over a wide frequency range, hence most suitable for audio applications. Its circuit is simple and has lower cost because it employs resistors and capacitors, which are cheap. The circuit is very compact, as we know the modern resistors and capacitors are extremely small and light. The voltage and power gain are low because of the effective load resistance. They become noisy with age. Due to poor impedance matching, power transfer will be low. Application: they have excellent audio fidelity over a wide range of frequency, therefore widely used as voltage amplifiers. And due to poor impedance matching, RC coupling is rarely used in final stages. Transformer coupled amplifier: here a transformer is used to couple between different stages. Its frequency response is this one. The gain of the amplifier is constant only for a small range of frequency, very small range of frequency. The output voltage is the collector current multiplied by the reactance of primary of the transformer. At low frequencies, the reactance of primary begins to fall, resulting in decreased gain. At high frequencies, the capacitance between turns of windings act as a bypass condenser to reduce the output voltage and hence gain. The amplification of audio signal will not be proportionate and some distortion will also get introduced, which is called as frequency distortion. Here the impedance of secondary of the transformer is made equal to the load impedance and primary impedance equal to the output impedance of transistor. For example, this is, suppose NP is the number of primary turns and NS is number of secondary turns. RL is the load here, then effective primary impedance RL prime is equal to NP by NS all square into RL. That's why it is calculated. Its advantage is excellent impedance matching, high gain, no power loss in collector and base resistors, efficient in operations, but it have poor frequency response. Frequency distortion is higher. Transformer tend to produce hum noise. Transformer are bulky and costly. Its application mostly used for impedance matching purpose, used for power amplification, used in applications where maximum power transfer is needed. This is the direct coupled amplifier. The first stage is with a PNB and next with an NPN. There is no coupling, it is directly coupled. Its advantages: circuit arrangement is simple because of minimum use of resistors. The circuit is of low cost because of the absence of expensive coupling devices. It cannot be used for amplifying high frequency. The operating point is shifted due to the temperature variations. It is used for low frequency amplifications, low current amplifications, etc. If we compare the three, RC coupling is used for voltage amplification, transformer coupling is used for power amplification, and direct coupling is used in extremely low frequency amplifications.